Hello everyone and welcome to part 2 of this week's lecture. In part 1, we looked at, for example, Bernoulli's equation and different forms of Bernoulli's equation. We looked at how we can write Bernoulli equation in the form of energy per unit weight or per unit volume or per unit mass, for example. And so in this lecture, we are now going to look at how we can apply this Bernoulli equation to solve fluid flow problem. Okay. And in this lecture, we are going to look at two different applications, that is the constant level tank and a varying level tank example. Okay. Let's have a look at it. So here we again have a Bernoulli general form of Bernoulli's equation, and when we derive this Bernoulli's equation, we made some assumptions that we have ideal fluid. It means that there are no viscous effects, and as such, there are no losses, and that means that the delta HF term that you studied in your previous lecture is 0. Okay, so no loss effect. Second assumption, we have incompressible fluid. It means the density is constant. And the last one, it is steady state. It means that there is no accumulation in the system or depletion in the system. It means that everything is running at steady state. Now let's look how we can use this equation to solve a system that is the case here, that is of a constant level tank. And so here you have a tank that has a cross-sectional area of A1, and then you have a hole at the bottom of this tank that is A2, and you are, for example, you have adjusted the flow in such a way that the level of this tank or the fluid in this tank, the level is constant, that is H1. So H1 is the height at point 1, and H2, that is the height at point 2, is actually 0. So it means that the difference between the 2 points is the height H1. Okay. So now the question is that what would be the volumetric flow rate of the fluid out of this tank? So we want to know what would be the velocity or the volumetric flow rate of this jet exiting the tank. So to calculate the volumetric flow rate, we have to look at the velocity. And to calculate the velocity, we use the Bernoulli's equation. Okay. So Bernoulli's equation, if we write it in the form of 0.1 and 0.2, so we have that these three terms are for 0.1, and then they should be equal to these three terms at 0.2, and that means that the energy is conserved, and because we don't have any loss term, so we consider that delta HF is 0. Okay. Now in this equation, as you can see, we have 5 variables, independent variables. It means and if you know your algebra, you know that we need 5 independent equations to solve this equation. So it means that we need to make some assumptions to simplify this equation, and that is what you will do always whenever you apply Bernoulli equation. You always try to make assumptions and then try to simplify this equation in less number of variables. The first assumption that we are going to make here is that U1 is equal to 0. And the reason for that is that the U1 is much less than U2 due to the reason that A1, that is the cross-sectional area of the tank, is much larger than A2, that is the area of the hole. And this comes from the continuity equation. And if you know that the continuity equation is U1 should be equal to U2 times A2, and it means that if your cross-sectional area is much larger than the area at point 2, the velocity at point 1, that is here, would be much less than the velocity here. Okay. And so you can assume, for example, you have an area of 1 meter square, and here you have an area of 25 centimeters square or 0.0025 meter square. So you will see that due to this area difference, your velocity at point 2 will be much larger than your velocity at point 1. Okay, so that is our first assumption. It means that we can consider U1 as 0, so we cancel out this term here. Second assumption, H2 is 0, and the reason we can say that because we have considered that the datum is at this point. Okay, so it means that the h2 is 0, and from this point, point 2 to point 1, we have a difference in height h1. Okay, and we can define this datum at any point. For example, we can define the datum here at the bottom, and then it means that the height at point h2 will not be 0, and it will be a positive value of h2, and then the height at point 1 will be h1 plus h2. Okay, so for example, in this case, to make our life easy, we just assume the datum is at point 2, as such h2 is 0. But you can do it yourself. You can, for example, after driving this equation, in the next case, you can consider that the datum is here, and you have a positive value of h2 and h1, and then you can drive the same equation and see if it makes any difference. Okay, it shouldn't make any difference because the height between the 2 points still be the same. Then we have the third assumption, or third point that we are considering, is that P1 that is equal to atmospheric pressure. It means that the tank is open to atmosphere, so the pressure is atmospheric pressure. And then we have another assumption that P2 is equal to P ATM, and that is a bit less obvious one, because there is always a confusion that why P2 is ATM. And the reason for that is that when you are inside this container, you have a pressure P2. As you go down, your pressure increases. But when you reaches at this point and the jet is going to exit the tank, all that pressure is going to convert from pressure head to velocity head, and that is why your velocity is much larger, because your pressure head actually gives increment to the velocity. Okay, and at this exit point, the pressure the fluid will feel is just the atmospheric pressure as well. Okay, because now this part is open to atmosphere as well. And as such, we can write that P1 is equal to P2 and is equal to ATM. And if we are dealing with our equation or with our system in gauge pressures, we can write that all of them are 0. It means this term will cancel out, this term will cancel out. Okay, so if you use all these assumptions and simplify this equation, we get this equation that h1 is equal to u2 square over 2g. And if you rearrange this equation, you get u2 is equal to square root of 2gh. So we know the velocity at this point now. And if we multiply this velocity with the area, that is cross-sectional area A2, we get the volumetric flow rate. And then we have the equation here for volumetric flow rate. And we can also calculate the mass flow rate. If we multiply the volumetric flow rate with density, we get the mass flow rate. And if you put the values of Q, for example, or U and A2 in this equation, you get the mass flow rate here. Okay. So this is, and here you have a nice simulation that you can try, for example, to play with these different parameters. For example, you can vary h1 or velocity h2 or the area of holes and see how they affect the volumetric flow rate or the mass flow rate. So please have a go at this simulation at this page. So we use Bernoulli's equation, and we said, okay, if we use this equation for an ideal, incompressible, and steady state system, we can get the volumetric flow rate from this a constant level tank. But what if we have deviation from these ideal conditions? Okay, so let's look at these deviations now. So first deviation that we can have is that actually we can have a real flow. It means that the first assumption that we made, that the viscosity effect is 0, is not true anymore. It means that we have this positive value of this delta HF. And what this delta HF means is that some of the energy that you are going from point 1 is actually being lost in the form of heat or in the form of friction. Okay, it means that if you now look at these two velocities, u1 and u2, so the velocity u1 must be larger than velocity u2, because some of the energy that you got from point 1 traveling to point 2 is going to be lost in the form of friction or heat. Okay, and one way of considering that loss or that friction is to include this delta HF term here. Another way of doing it is actually, and you will look at this delta HF term in much more detail in the next lecture with Dr. Tom. Another way of doing this or to account for this energy loss is to use what we call discharge coefficient, or we multiply your actual velocity with some coefficients to consider the effect of viscosity. So what kind of these effects can be? So there is what we call, for example, velocity coefficient that accounts for the effect of viscosity on your fluid. And then you can have also some other coefficients to correct for non-ideality in your system. Is, for example, if you have a sudden contraction. So if, for example, you are going from a very large cross-sectional area into smaller cross-section area, and because the fluid is being constricted in this area here, so that is also going to generate some energy loss in the form of eddies or in the form of the contraction. And then we can correct this, for example, ideal velocity by multiplying with contraction coefficient as well. Okay. And as you can see here, the contraction coefficient is actually the ratio of the area of the jet to the area of the hole. Okay, so area of the jet is here and the area of the hole is here. So if you take the ratio of the two, you get the value of contraction coefficient. And if you have more contraction or more, for example, kind of geometry where you lose a lot of energy, for example, here you have much smooth edge, while here you have very sharp edge for the fluid to go from a 90-degree angle. So there you have much higher contraction coefficient compared to when you have a very smooth edge. Okay. So the typical values of CV, that is the velocity coefficient that considers viscosity effect, is 0.98. And the typical value for CC is 0.65, but they both depend on the geometry and the type of the fluid. Now we had this ideal flow rate that we got for case 1, where we are not considering any viscosity or contraction effect. And then you have the real mass flow rates, where actually you multiply this ideal mass flow rate with these two coefficients. Okay. And very often these two coefficients are lumped together in a form of another coefficient, that is CD. So CD actually is equivalent to the multiplication of CD. But although it seems like this is the multiplication, but it is not entirely true, because CD can be different than the multiplication of these two coefficients. But in most of the cases, they are like that. So all these coefficients, we determine them experimentally. There are no theoretical basis for these coefficients. Okay, so you have to rely on experiments to determine what CV and CC values are going to be, or CD values are going to be, and then you multiply your ideal velocity with these coefficients to get the actual velocity from your system. Okay. So here you have the mass flow rate, and if you again divide it by density, you get the volumetric flow rate. So here that is CD, it should be in subscript. And then if you divide with the cross-sectional area, you get your U2, that is the non-ideal or real mass velocity of your system. Okay. And the CD value is less than 1, and typically the value of CD is 0.6 to 0.7. Okay. So this CD is a coefficient to account for the non-ideality of your system. And then you have the second deviation. You have, for example, you can have a compressible fluid. It means that the density is no more constant anymore between 0.1 and 0.2. So you have rho 1 at 0.1. And when the fluid is moving, for example, from 0.1 to 0.2, it is being compressed, or it is changing its density. And then you have to use the density at 0.2, that is rho 2. Okay. And the third deviation can be that because we assume in the original or on the journal form of Bernoulli's equation, we assume that we are steady state, but you might be in a situation where you are at unsteady state. It means that the properties are changing with time. and you have either accumulation or depletion of within the system. Okay, so let's look at this this third, for example, deviation with an example. So previously we looked at, for example, the case of a constant tank, and by the nature of the problem, we said that we are maintaining a constant height inside this tank. Okay, and from that we got the velocity u2, that is cd times 2gh1, the volumetric flow rate and the mass flow rate here. Okay, but now let's imagine that the area is not constant, or sorry, the height is not constant anymore. It means that the level within the tank is going to change. Okay, and then we have the case here where you are not filling up this tank anymore, and you have the fluid is exiting from this smaller or narrower hole, and as such the height is going to decrease in time, okay, till the tank is completely empty. If that is the case, we have to again start with the generalized mass conservation equation. So that is mass in minus mass out equal to the rate of change of mass in the tank. Okay, we have mass in 0 because there is nothing that is feeding in the to the tank. The mass out is the volumetric flow rate, that is rho, sorry, mass flow rate, that is rho times u2 times a2, and these two should be equal to the rate of change of mass in the tank, so that is rho a1 h1, and you are taking the change in mass per unit change in time. Okay, but again, if we assume that u1 is much less than u2 based on the continuity equation and the values of a1 and a2, we get the same relation for u2, sorry, that we saw previously for the case of constant tank. But now the difference is that instead of having h1 constant like it was the case here, we had just h1, but now we have h1 minus h2, and we can write it h1 minus h2 is just h. Actually it means the change in height with time, so we can write that the u2 is equal to cd times 2gh1, sorry, h, and h is changing. It means with the change in the height, velocity is going to change. Okay, and we can put the value of u2 from this equation here to this equation. We have we get this final equation, and if we now rearrange this equation slightly, so we can write it in the form of dh over square root of h times for example a2 cd square root of 2g over a1 dt, and we can take integral on both sides. So we integrate on the left hand side from h1 to h2. It means h1 to h2, it means that from top of the tank to the bottom of the tank, and in time 0 to t, because when time is 0 the level is at height h1, and when time is t the height is h2 in the tank. Okay, so if you do the simple integration, you get this equation in the form of t, that is t is equal to for example a set of constants times the square root of h1 minus h2, and in our case we know h2 is 0 when the tank is completely empty, so I wrote te. E means the tank is time to empty the tank, so we put h2 0, so we get this final equation here. It means that the time for example is a function of height. Okay, so if you double the height of your fluid in your tank, you are going to get a 41% increase in time. The reason that the square root of 2 is 1.41, it means you will get 41% increase in time if you double the height. Okay, and again I put a simulation on your Blackboard page where you can actually, yeah, so you can for example use the water tank here, and you can actually play with the speed, for example how the speed is changing when for example the area the level of the tank is constant, and if the level of the tank is actually changing, for example. Okay, so have a look at it and try to understand this concept. And that's all for this part. And in the next part, we will look at different flow measurement devices that are based on the principle of Bernoulli's equation. Okay, thank you for your time.